Okay, now we're going to look at some dihybrid crosses. And remember, dihybrid crosses, crossing two individuals with contrasting forms of two traits, which means we're dealing with two genes, which means we're dealing with four alleles. So things become a bit more complicated now. And here is my little card with dihybrid cross ratios. First, we'll do the regular one with the 9:3:1 ratio, then a test cross, and we'll do an example of an epistatic cross. So, go cross rental generation. Plants that have purple flowers and are tall in stature. Gene A controls flower color, the gene B plant size. We'll cross them with plants that have white flowers and are dwarf in size. Recessive traits. X. So F1 or first filial generation, big A, this parent, a little a from that parent, a big B from this parent, and a little b from that parent. So their genotype is big A, little a, big B, little b, and they will all be purple and tall. We'll cross the F1s or self them since we're dealing with plants to get an F2 generation. And the F2s will show 9/16 being purple and tall. That's what the PT is for. And they will have big A for purple, big B for tall. The second alleles don't affect the phenotype. See this okay? 3/16 purple dwarf. The other 3/16 will be quite tall. And then 1/16 will be D for purple tall, purple dwarf, excuse me, WT for white tall, and then white dwarf. 1/16 are little a, little b, or double recessive. So let's do a Punnett square. Now the Punnett square is going to be a bit bigger and a little more cumbersome. Work on that here. So crossing two F1s that are said to be heterozygous dihybrids. They're heterozygous at both these genes. And there'll be 4 gamete classes for each. So remember, each gamete's got to have one A and one B. So about a quarter of them will be big A, big B, quarter big A, little b, quarter little a, big B, and a quarter little b. And the same down the sides there. And so now we fill that in. Some of you may have learned the FOIL method, first outside, inside, last. If that works for this, by all means, please use it. Anyway, so what goes in here are all caps. Way done. Little a, big B. Little a. Quarters of the way done. Now we just have the last row to do. Little a, B, little b, little a, little b, little b, little a, little a, b, little b, little a, b, little b. So on the lower right, this one is the double recessive. Okay, now let's add phenotypes to these boxes. So 2 big letters means purple tall. So we'll just call that PT. So we have PT here, PT there, PT, T, PT. Aha, here we have purple dwarf. PD, tall, purple dwarf again, PD, tall, tall, white, tall, white, tall, purple dwarf, sorry, purple tall, there's purple dwarf, white, tall, and white. Cool. So that's our Punnett square with the phenotypes added. Now if we count them up, you can see where we get this 9-3-3-1 ratio. So it should be 9 purple talls. 1, 2, 3, 4, 5, 6, 7, 8, 9. Should be 3 purple dwarfs. 1, 2, 3. There should be 3 white talls. 1, 2, 3. And then our single white dwarf. So that's where this 9-3 to 3 to 1 ratio comes from. Okay. Numerators of these fractions. So things are in 16ths because in a dihybrid cross, of course, you end up with 4 on a side, and 4 times 4 is 16. Okay, let's look at a dihybrid test cross now. Again, this white dwarf one is the tester, homozygous recessive and true breeding. So all of its gametes are going to have the little a and little b allele. This guy can produce, just like over here, 4 different gamete types. Quarterly gametes with big A, big B, big A, little b, little a, big B, little a, little b. So again, our Punnett column, if you will. Let's fill that in. Big A, little a. B, and little a, B. Be in about equal numbers, so a quarter of these things, oops. A quarter will be purple tall, another quarter will be purple dwarf, another quarter will be white tall, and another quarter will be white dwarf. And so that gives us the characteristic dihybrid F2 phenotypic ratio of 1 to 1 to 1 to 1, which is characteristic of a dihybrid test cross with approximately equal numbers of offspring in all four phenotypic categories. Okay, let's try the hybrid cross now that shows epistasis, where one gene is blocking expression of another gene. I'm going to take 2 strains of mice, black strain and an albino strain. Times albino. The black mice, little a, big C. The albino mice are big A, little c. And then our F1s, of course, are going to be big A, and big C, little c. But their phenotype is going to be the brown wild type that is referred to as a goody. Just means that each little hair has different colored bands in it, but the overall appearance is a brown mouse. Now we're going to take and cross 2 F1 agoutis, and we'll see we get a F2 phenotypic ratio where 9/16 will be agouti, just over half. B/16 black. Again, dashes mean that that allele, doesn't matter what it is, it doesn't affect the phenotype. And then 4/16 or 1/4 would be white or albino. Those are C, little c, and it doesn't matter what the A's are doing. The little c allele is blocking the pigment deposition in the fur, so the mouse ends up being white. So let's go ahead and do a Punnett square of this to see how we get this 9:3 to 4 ratio and figure out what type of epistasis we're dealing with here. So crossings, little a, little c times little a, little c, across the top, c, little c, big C, and little c. Four ways that the A's and C's can combine. You have to make sure each gamete has a single A and a single C in it, and no more than that. Same thing going down the side. Big C, big little c, little a, big C, little a, little c. So filling in the blanks, can we see this square? Okay, I guess now we can. So we've got all bigs in here. Okay, little c, C, little a, C, C, halfway there. Big A, big C, little a, C, little a, big C, big C, little a, big C, little C, big A, little a, big C, big C, big A, little C, so, done that correctly. There's all our genotypes. Now let's add phenotypes to them to see how we get this ratio. So let's AG for a goody. W I'll use for white instead of albino. Goody, white. Goody, black, black. Goody, white, black, and white. Counting through these, we should get 9 agoutis. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's our 916 brown wild type or agouti. We should get 3 black. 1, 2, 3. 3 16ths black. Every time there's 2 little A's and a big C, we get black. And then there should be 4 whites. 1, 2, 3, and 4. So every time there's 2 little C's, no pigment is deposited in the mouse's fur, and it ends up being white. And so this is an example of recessive epistasis, because it's the recessive alleles, the little C's that are preventing the pigment deposition. So that's how we get this 9 to 3 to 4 F2 phenotypic ratio. In 9, 3, and 4 add up to 16, again, because it's a modified dihybrid cross. So the last thing I want to show you in this unit is a chi-square test using dihybrid cross. So let's move on to that. Remember, this is called chi-squared goodness. Test. Discriminating between the null hypothesis, of no difference, observed equals expected, versus the alternate hypothesis that just states the observed does not equal the expected. Remember our chi-square formula. Summation of the observed minus the expected squared divided by the expected. This example will utilize the comb shape or morphology of chickens. So chicken combs, we could cross 2 individuals with walnut combs. see our phenotypic data. We'll put over here. So for dihybrid cross, now we're going to get 4 phenotypes, 4 phenotypic categories: walnut cones, rose cones, pea cones, and lastly, single cones. Total. So this cross yielded 7 little chickens with pea cones, walnut cones, 1 rose, 30 with pea, and 12 with single, which comes total to be 160. Okay. So this is our observed numbers. This way, our observed numbers for our data. Expected proportions. Assume, or we think, hypothesize that this is a dihybrid cross with complete dominance, then 9/16 walnut, 3/16 should be rose, 3/16 pea, and 1/16 single. Okay. And now what we do is multiply our fractions by our total to get our expected numbers. 9/16 times 160, it's 90. 3/16 times 160 is 30, and 1/16 times 160 is 10. Add them up, and they come out to be 160. So our next row, remember, is the observed minus the expected. So that's -3, 1, 0, and 2. And then we take those numbers, square them, 9, 1, 0, 4. And then the next step is to divide them by the expected numbers. So observed minus E squared divided by expected. And so that's 9 divided by 90. It's 0.1. 1 divided by 30. 0.033. 0 in that column. And then 4 divided by 10 is 0.4. And then to get our, see all these? Yes. Good, good. And then we add across the columns to get our chi-square value. And that comes out to be 0.533. So chi-square sub c value. And now we compare it to the value in the table. This time, degrees of freedom is going to be different. 4 phenotypes minus 1 equals 3. So now we go down to the third row in the table on page 68 of our textbook, and that is 7.815. See that our value from the table, 7.815, is larger than the value we calculated, 0.533. So that means we failed to reject our null hypothesis. So that is our conclusion. Okay, so in an examiner problem, I want to see a conclusion written in the form of failing to reject or rejecting the null hypothesis. Again, when the number we calculate is bigger than the number in the table, that's when we reject the null hypothesis. and we're forced to conclude that our data is not supportive of the theory. In this case, the theory is a 9:3:1 ratio coming about from a dihybrid cross. You can see our numbers are very similar between observed and expected numbers. And so with that, that ends our discussion of dihybrid crosses. Please feel free to contact me if you have any questions.